Okay, student, here we shall see another topic, that is Ampere Circuital Law. So this Ampere Circuital Law, it is actually the alternative of Biot and Savart law. If you remember, in Biot and Savart law, we are using to find a magnetic field. Okay, so Biot-Savart law, it is actually a law which enable us to find the magnetic field due to a conductor carrying current. So in the alternative way, I can say that this magnetic field due to a current carrying conductor can also be determined by amperes. So according to this Ampere Circuital Law, it says that the line integral of the magnetic field around any closed loop is equals to mu naught times the total current enclosed by the loop. So that is the statement of the Ampere Circuital Law. So if you write this law in the mathematical language, or we can say in the mathematical equation, this line integrals mean you integrate of b over small length dl, and that will be equals to mu naught times the total current enclosed by the loop. Okay, so please remember that this mu naught here, it is the permeability of free space, which means if this is my conductor, let's say it carries a current I in the upward direction. Now this conductor, in this case, let's say it is lying in free space or in vacuum. So if it is in vacuum, then I have this mu naught, because mu naught, it is actually used when the medium is vacuum or free space. Alright? Okay. Now, why do we have this? What is the meaning of this line integral b dot dl? The meaning of this line integral b dot dl, it means that, because if you remember, when a current is passing through a conductor, then the directions of the magnetic field passing through such a straight conductor can be determined using a thumb rule, a right hand thumb rule. So if your thumb point in the directions of current, then your call fingers will give the directions of magnetic field. So look at my call fingers. These are my call fingers. So these call fingers here, right, they are actually, circulating, or we can say they are surrounding the conductor carrying a current I. So because the magnetic field in this case, it is circulating, right, over the or around the conductor. So that is why this line integral, sometimes it is known as the circulating magnetic field. Okay, all right. So let us come to the proof of this law. Okay, so here for the proof, I will consider a straight conductor carrying a current I in the upward direction as shown in figure. You know very well that this straight conductor carrying current always produce a magnetic field, right, at some distance from itself. Let's say this is a point P. Then at point P, you'll have a magnetic field. And where is the direction of this magnetic field at a point P? So that direction, it is actually tangent to this point. That means it is acting up. Alright. Okay. Now, over this point P, we will consider a small elemental length, that is dl. So this dl vector, right, it is also pointing up, which means the angles between B and dl in this case is 0 degree. What is the angle B and DL in this case? 0 degree. Alright. Now, further I will imagine that this point P, let's say it is at the distance small r, okay, from this straight conductor. Okay. So if that is the case, then what happened? This Biot and Savart law, actually they have found that the magnetic field at a point P due to a straight conductor carrying current is B equal mu naught I upon 2 pi r. This is found by Biot and Savart law. Okay, but for this equation, right, we have not done yet because this is not included in your syllabus. But just remember this equation. When you find the magnetic field at any point due to a straight conductor carrying current, then that magnetic field, it is equals to mu naught I upon 2 pi r, where r is the distance of the point P from the straight conductor. So this magnetic field is equal, the magnitude of this magnetic field, where B is equals to mu naught I upon 2 pi r, it is not just only at this point, but the magnitude of this magnetic field, it is the same at this point, at this point, at this point, at this point, right? At any point on the circumference of the circle, right? As long as these points are at the same distance from the conductor. Okay. So, if this is the magnetic field at a point P, okay, due to a straight current carrying conductor, then let me find out what will be the line integral of B dot dl. Now this B dot dl, it means B dl cos theta. And what is theta? Theta is the angle between B and dl. So again, I have already mentioned before that the angle between B and dl is how much degree? 0 degree. Because if you consider any elemental length, right, along this closed loop, then that angle is 0 degree. Okay. So when theta is 0, then we know cos 0 is 1. So 1 times BL will be just BL. Okay. Alright. Now what is B? Is it over this closed loop, is this magnetic field uniform or not? The answer is yes. The magnetic field along this closed loop, it is always the same. That is this much. It does not change because all these points on the loop, they are at the same distance r from a straight conductor, which means if this is my straight conductor carrying a current I in the upward direction, now this is the magnetic lines of force. So the magnetic field at this point, at this point, at this point, at any point, right, on this circumference of this circle, it will always be the same because the distance of all these points on the circle, it is same. Okay. So the B here, it is constant. So if it is constant, then I'll take it outside the integration sign, and inside I'll have only dl. Okay. Now, what is this integrations of dl? When you integrate, it means you are finding the total values. So when you integrate this small dl, that means you are finding the total length of the loop. Now, what is the total length of the loop? The total length of the loop, it is actually, right, the circumference of the loop. So, if you integrate dl, you will get 2 pi r, which is the circumference of the loop. Okay. So then, now, look here. We have the line integral of B dot dl is equals to B times 2 pi r. Okay. So my aim is I want to prove these equations of Ampere Circuital Law. So therefore I can see here that this line integral b dot dl is equals to how much? B times 2 pi r, which mean instead of b I will write this value, which is the magnetic field at a point P due to a straight current carrying conductor. Okay, in this way. So this 2 pi down, 2 pi up, cancel. So finally you will have the line integral of the magnetic field over this closed loop is equals to just mu naught I. Okay, so this is nothing but the Ampere's law. Line integral of magnetic field is equals to mu naught times I. What is I? Now look here. This I, it is the current. Look here. If this is my conductor, this is my closed loop. Now this conductor which carries a current I, now this current I, it is being enclosed by the loop. Okay, so this I here means it is the current which is enclosed by the loop. Okay, so please note down that this total current this current I, you may not have just one conductor which is passing through the loop, but sometimes you may have like 3 or 4 conductors. Let's say this is carrying I1, this carries a current I2, this is I3, this is I4. Now, if I draw any loop around any conductor, okay, let's say I draw a closed loop over the conductor I2 and I3, then this I, it means the algebraic sums of the current, okay, which is enclosed by the loop. So in that case, right, looking at this figure, this I means it is actually the sums of I2 and I3. I2 and I3. Why? Because these two current, I2 and I3, they are enclosed by the closed loop. But however, the current I1 and I4, they are outside the loop. So that means we need not to consider, or we need not to take these current I1 and I1 and I4 in this case. So my total current, as I have written here, summation over I, it means the total current enclosed by the loop. So if the loop encloses two currents, then I'll write I is equals to I2 plus I3. Alright? Okay. So this is how we prove the Ampere Circuital Law. And another point that you have to note down here is this Ampere Circuital Law, it is actually applicable when this current which is enclosing by the loop, it is a steady current. Okay, that means this current should not be fluctuating. If the current is fluctuating, that means this Ampere Circuital Law, right, it will not be applicable for such type of conductors carrying fluctuating current, but the current has to be steady. All right, so this is all about Ampere Circuital Law and its proof. And in the next lecture video, we shall see about the applications of Ampere Circuital Law.